Right, we'll get started again. We'll actually bang on time. So again, that's the package that contains a copy of the slides and a copy of the tutorial exercises. Just as an aside, so again, when you think about efficient R programming, you automatically start thinking about speed of execution. You think efficient, must want my code to go faster. But there's lots of different things with speed of execution. If that's all you cared for, R's probably not your best language. If you really cared about speed, then use C or C++ or something else. R's got other things. And this little bit of code here, so I don't know if you're familiar with Drat. Drat's a really cool package, and it allows you to create your own package repository. So CRAN is a package repository, and it contains lots and lots of packages. Drat allows you to create your own repository. So for all the courses that we teach, we put all packages in that repository. And it's hosted in GitHub, and we've got it set up to link with Travis. So Travis is something called continual integration. So what that means is when you push a commit to Git, Travis runs off and does some stuff, right? Checks your package builds. And we've got it set up that you push a change to your package, Travis goes away and does its thing, and if my package is correct, it automatically updates the package on GitHub. Right? So if I find a typo in my slides, I just need to change them, push it to Git, Travis will run for 2 or 3 minutes, and then the repository is automatically updated. And in terms of saving time, that works out huge, especially if you've got lots of these packages for teaching or perhaps internally. It's much more than you could possibly save. Well, it makes your day a lot nicer. Right? You're not having to sort of manually add packages. You're not trying to share packages. I've now got one place where all my code's kept. I can share it with everyone in this room, and it doesn't take that much effort. Right? Whereas done badly, it could be a huge time sink. Right? You might have to sort of commit here, left, right, and center. Right? So there's lots of ways of when we think about efficient programming. It's not just speed of execution. It's sort of general day-to-day coding. Are we doing something that could be optimized that saves us 5 minutes a day, 10 minutes a day? Right, so we're going to go on. Oh, these are the exercises for I think I can make this bigger. It's in the package. Oh. These are the exercises that were for the last part. I'm not going to go through them. As I said, I'll add solutions. But there were 2 exercises. One was reading in a CSV file. Okay, so you've got a big CSV file, you want to read it in, and you could try and use read.csv or the RDS, that's R's binary format, or read_CSV from the reader package, or fread from data table. Right? And so again, you've got a variety of solutions, and it's not that hard to time these solutions, compare and think, and come up with, well, which one's fastest? If one's faster than another, well, is there a downside? Right? Now, would you believe that read.csv is the slowest out of all of them? No. But the bright side is I've got code from 2000 that's using read.csv and still works. Right? So if you've got 10 rows and 5 columns, do you need to get an external dependency? Perhaps, perhaps not. Right? But just sort of take time to think about, what's the upside, what's the downside. And exercise 2, it's more about selecting columns from a data frame, and some ways are slow and some ways are fast, and just to try and get you to understand what's going on. And to be honest, once you walk through a bit of code, it should probably become clear of, yeah, I can understand why something's slow and why something's fast. Right? And it's usually to do with types and object sizes. But I won't go through that anymore. As I said, the tutorial is part of the package, and I'll upload solutions. Let's be honest, it's not going to happen tonight, and probably not tomorrow night either. We'll give it a Thursday night at 50-50 chance, okay? That's the best you're getting. But by next Wednesday, at the latest, it should be there. Probably. Right. So, parallel computing. So the purpose of this section, if you've done parallel computing in R before, sorry, this section is going to be dull. The aim of this section is you've not done parallel computing, you've heard of it, but you're not quite sure what it is, or even how to do it in R? Is it worthwhile? So what we're going to try and get at is have not many slides. You'll get a feel for what's going on. You'll have a bit more of a meaty tutorial exercise. So rather than 2 minutes, it's going to be maybe 10 minutes or 15 minutes to get a feel. And then at the end of this section, you'll be able to go away and think, yes, I can use parallel computing, or no, it's going to be a waste of my time. And if you've only spent 40 minutes and decided it's a waste of your time, then that's good, because it could take you 1, 2, 3, or 4 weeks to come to the same conclusion. So it's to try and give you a flavour, to see what's going on, and if it's useful, then there's lots of resources. So as I said, I think there was a session this morning that dealt just with parallel computing. Right? We've got a small amount of time. So, parallel computing. So this is a nice little graph. So what's going on here? On the x-axis, we've got time. So we're starting off at 1980, and I think we're finishing around about 2012 is the last year. And on each dot represents a particular CPU. So that's the brains of your computer. Right? So Intel, Xeon, that sort of stuff. And on the y-axis, we've got clock speed of the CPU. And if I wave my hands sort of a bit, just sort of think of clock speed as how fast the CPU is going to do a calculation. Right? It's a bit more complicated than that, but as a first order, it's more or less there, so we'll just pretend it is. Right? And so x-axis, we've got time. Y-axis, we've got essentially speed of your computer with a bit of waving hands. Right? And you can see that from 1980 to around about 2005, we got a nice increase. Okay? So I did my PhD around about 1999 to 2002, and we had a computer lab, and whenever we got a new computer, everyone would rush and fight for it, and it would be survival of the fittest, because your code just went faster. Right? You got a significant boost. So it was the only time I started going in early was when we got a new computer. Round about 2004, 2005, it plateaued. Right? Now, there's still been, computers are still faster than they were a decade ago, so that's what I mean. This is sort of the speed, right? It's not a complete measure. But round about 2004, the speed essentially plateaued for the most part. And the reason for that is physics, and physics is just a pain in the rear end, and things just got hot, right? So if you've got a laptop and your thighs started to get warm, that's because your computer's doing too much work, your fan can't go fast enough, and so it's just a bit of a pain. And so around about this time, 2005, manufacturers started thinking of, well, rather than trying to get eke out each little bit from a single processor, we'll go parallel. Okay? So, now most people have dual core, 2, quad core, 4, 8 core machines. Your laptop's probably got 4 cores. Right? These things are now just ubiquitous. Whereas when I did my PhD, I don't think any of our machines, and they were not cheap things, were anything other than 1 core. Right? So every laptop in this room, I suspect, has got more than 1 core. And, manufacturers didn't go into parallel computing for us, scientific community. They went in for the whole market. And so we're just trying to piggyback on top. So there's a few parallel packages kicking about. So if you look at the CRAN task view for high-performance computing, you'll get different ideas. What we're going to look at this afternoon is multi-core or shared memory. Right? So that's parallel computing on your laptop, on your desktop, on your machine. Right? You've got one machine. You're not talking to other machines. It's just using all the cores on your machine. Right? And the crucial thing is you might have 8 cores, but they can all share the same memory, so we don't have to worry about transferring memory and transferring information because they all have potential access to the same thing. Okay? So that's what we're going for. So, quick exercise. Everyone's got the parallel package. I think that came with, I think it was around about 2013 as well. And there's a function in the parallel package called detect cores. So if you run those 2 lines of code, it'll tell you how many cores you have on your laptop. So I'll give you 30 seconds. Or maybe a minute, just to sort of fire up to see how many cores you've got before we get going. So, I presume no one's got 1 core. I don't want to name and shame people with only 1 core. It's not anything to be embarrassed about. 2 cores, does anyone have a dual laptop? Nope. 4 cores? 8 cores? 16? Not seen a 16-core laptop yet, but don't know if it exists. So, between 4 and 8. So, I've got 8 in my laptop, but it's a pretend 8. So I've got an Intel chip, as most people probably have around the room. And Intel play a funny game. So when you type detect cores, what R's doing there is it's asking the operating system how many cores do you have. And so there's a degree of trust, and people lie, and computer chips lie. So Intel use something called hyperthreading, and so my machine has 4 physical cores and 4 sort of cores that are somehow magical and come into existence. And so my 8 isn't really 8, it's more like 6 and a bit when you sort of start testing it. And I suspect most people with 8 cores are in the same situation of you don't really have 8, you've probably got 6 and a bit when it comes down to sort of raw computational power. But that's Intel playing the hyperthreading game. Right. So what we're going to do is we're going to think about, can your application be run in parallel? And then give you an example, and then let you do your own, let you go through a tutorial. Okay? So, a nice, easy rule of thumb. So what we're going to think about here is we're going to think about a for loop. So we've got a for loop in your mind, and you want to be able to run that for loop in parallel. Okay? So, let's have a thought experiment. Let's suppose I've got 10 numbers. Okay? And I'm wanting to calculate the mean. And I just happen to have 10 volunteers from the audience to help me with this tough calculation. How could I do that in parallel? It's not really an easy way of doing it. Now, you can do it, right? You know, you could sort of give 5 people 2 numbers each, and they could each do, you know, add in the 2 numbers and then run to the front and give me the answer, and then I could combine them. But you could think of, well, I could have just done that quicker myself rather than getting people to help me. All right? So not everything can be run in parallel. A nice, easy rule of thumb is, can you run your for loop forwards and backwards and still get the same answer? Right? So if you've got a for loop in mind, you're thinking, I wonder if this is suitable for parallel programming. Can you run it forwards, and can you run it backwards? Right? So what do I mean by forwards and backwards? Forwards would be going from 1 to n, backwards would be going from n to 1. So if you've got your for loop, can you change the 1 to n to go from n to 1? Right? And do you still get the same answer? Right? And if you still get the same answer, it's almost certain that you can run it in parallel. So here's a little noddy example. And the idea here is that A is a vector and B is a vector. Okay? So A and B are just vectors of numbers. And what happens here is that when we go from 2 to n and n to 2, we're going to get different answers. Right? So when I is n, when we're going backwards, we've got ai minus 1, so that's an minus 1, and that equals an. But when we go the other way, we're going to get out of sorts. Right? So running this thing forwards and backwards isn't quite going to work, because here an equals an minus 1, an minus 1 equals an minus 2, an minus 3 equals an minus 4, and when we swap the order, we're going to get a slightly different answer. So that's sort of not good. This loop is perfect, right? So this is sort of the nice, easy, low-hanging fruit, right? So if you're doing Monte Carlo simulations, so Monte Carlo simulations are bootstrapping, for example, cross-validation, the little example where we're throwing darts, right? So if you think back to the darts example, does it matter if I throw dart number 1 before dart number 2, or can I go swap the order? So in the darts example, I can throw darts 1 to n or n to 1, and I still get the same answer. It's a for loop I can write forwards and backwards. And it's essentially a Monte Carlo simulation. So it doesn't matter if we go from 1 to n simulations or n to 1. You're still going to get the same answer. I know there's random numbers going on. We ignore that. Another one that runs in parallel is if you can use the apply function. Right? So what's the apply function? The apply function is something that will apply a function to each row or column of a matrix. Right? So if you're working at column sums, for example, does it matter if you work at the column sum of row 1, or column 1, column 2, column 3, or column n minus 1, n minus 2, n minus 3? You can run forwards, you can run backwards, it doesn't matter. So when you're running things in parallel, it's guaranteeing the order is the tricky part. Right? Because what's going to happen is we've got a bunch of jobs, and we're going to send them out to the computer to let them run, but we don't know if job number 1 is going to run before job number 2, job number 2 is going to run before job number 3. We don't have control in this particular framework. Right? So what we're looking for is nice, simple situations where we can simulate bunches of things and then gather in the results. And the standard apply family has parallel replacements, right? So if you can write your code using lapply, apply, or sapply, it must be able to run in parallel, right? You don't need to think. So if you've got a list and you're doing parallel apply, it must be able to run in parallel, right? End of story. If you can write it as a par-sapply, so it's a fancy way of doing a for loop, it must be able to run in parallel. If you can use apply, it must be able to run in parallel. Right? So what's nice about this stuff I'm talking about today is the overhead of trying it out is quite low. Right? You're not going to have to go and change a massive code base. You can spend 10 minutes, run it in serial, run it in parallel, do some timings. If it's good, happy days. If it's bad, well, you've wasted 10 minutes. You can go to the pub and drown your sorrows. Right? So it's quite low-hanging fruit. This stuff also today that we're talking about is platform independent. So it'll work under Windows, it works under Mac, and it works under Linux as well. Okay? So you get other versions that are more platform specific, but here we're looking at the more general one, which is easy to implement, and we're not having to worry about the platform. Right? You don't need to care about what your user's using. It just works, which is nice. So let's have an example. So Monte Carlo simulation. So let's suppose we've got an example like this. Okay, so I've started off creating a vector, and I'm going to stick my results in this vector of length n. So I'm going to do capital N simulations. So that might be 10, it might be 100, it might be 1,000, it might be 1,000,000. And then I'm going to do a for loop, 1 to n, and I'm going to do in each iteration, I'm going to do a Monte Carlo simulation. Right? And hopefully that's relatively obvious of why we can run that in parallel. Because if I had n processes, so let's suppose we're doing 10 simulations, I've got 10 processes, each processor could do its own job. Right? They could do them all completely independently, and once they've finished, they would give me back the result. What sort of speed up would you expect from that? That's hard to tell. Let's suppose your Monte Carlo simulation took an hour. Well, each processor spends round about an hour doing its job and gives you the answer back. So you're getting sort of a tenfold speed up. But if your Monte Carlo simulation took a second, half a second, excuse me, then the overhead of communication is going to be a pain. Right? And the same way, if I gave each of you a job, got you to run it, and then give me back the answer, if the overhead of me talking to each person in turn outweighs the overhead of you actually doing the work, what's the point? Right? So it's the same idea in parallel computing. Right? If these little Monte Carlo simulations are just simulating a normal, then don't do it. Right? The thread communication is going to outweigh. Now, so I've talked about cores, I've talked about threads. Sort of a way of getting your head around this is that your computer is very smart. It always amazes me at how smart computers are. And it gives you the appearance that it's doing lots of things at once, whereas actually it's constantly shuffling what it's doing. So each job has got a particular thread, but you've only got 4 or 8 cores to do the jobs, and so it's doing, it's being really clever of what it's doing. So it's given the impression that it's doing things, but it's still limited by the number of cores. So let's move this to parallel. So we start off with this little bit of code, and then we're going to rewrite it as sapply. So sapply is we're going to apply a function to each element of a vector. Right? Apply is applying a function to each element, or each row or column of a data frame, or matrix, sorry. Lapply is applying a function to each element of a list. Sapply is applying a function to each element of a vector. And here my vector is 1 colon n. So we're going to apply the function MC to 1 colon n. So all that's going to do is do capital N simulations. Right? So if capital N was 10, we would have 10 independent Monte Carlo simulations. Writing it as this is going to be done in serial. So we do simulation number 1, then simulation number 2, then simulation number 3, then simulation number 4, then simulation number 5. Okay? Using sapply isn't faster than a standard for loop, just in case you're wondering. Or at least it's not worth getting your knickers in a twist, so to speak. How do we make it running parallel? Right? So this is our code here. This is my one line, and I'm wanting to change this to run in parallel. Right? Well, I've added in a couple of extra lines. So in line 1, I've created a cluster. Right? So this is from the parallel package. So I've had to load the package beforehand, so library parallel. Then I've made a cluster. The number in the brackets refers to how many cores or how many threads we want to generate. Okay? So here I'm going to run using 2, so the potential for 2-fold speed up. Typically what I do is if I've got 8 cores to play with, I'll knock one off, so I'll go down to 7. And that would allow me to still check emails and look at Facebook and mess about on Twitter and all that waste of time that we do. If I'm going away for the night, then I'll bump up the number of cores. You can have any numbers you want in here, but it's not magic. So if you've got 8 cores and you put 100, it's just going to go slower. Okay? So we're making a cluster, and the way of thinking about this little thing is, in CL we've got a copy of R running two separate R processes that we're going to create. Then we've changed sapply to par sapply. So notice the PAR at the start, and also the capital S. The function call is identical, except for this, we've got an additional argument in the first line, in the first argument. So we've got CL. CL is that thing from make cluster. Okay? And then we're quite nice, and we're going to clean up afterwards, and we're going to stop the cluster. Okay? If you don't do the last one, at some 5 minutes in the future, you'll get a sort of a warning message saying closing localhost, blah, blah, blah. Okay? So it's not a big deal if you don't, but you should, because it's nice and friendly. And that's it. Okay? So to check that it runs in parallel, we've gone from this one line, okay, we've got a couple of lines, but we can now think about, is it faster? Right? You know, we can use system.time or the micro benchmark. Right? So it's not a big overhead of trying this stuff. Typically what happens is that the thing you're trying to run in parallel has a parameter you want to change. Right? So it could be the number of columns in your data frame, or the number of rows in a matrix, or the number of elements in a list, or here the number of simulations. Right? And depending on the value of that parameter will determine whether or not running in parallel is worth it. Right? So here, let's suppose n is 4. Right? We've gone to the whole hassle of setting up this cluster and stopping the cluster and creating 4 threads and then gathering all the results back, and that takes time. Not a lot of time, but it takes time. But if running your Monte Carlo simulation took an hour or 2, then that time's worth it. Right? Likewise, if your Monte Carlo simulation took half a second, but you're doing 1 million of the silly things, then again, going to 4 cores is worth it. Right? So you've got that sort of little calculation in your background of, it's not going to be, it's either good or not, it's either good or bad. The answer is going to depend on some parameter, and that's just the way life is. And so you need to think, what values are you thinking of? Okay. As an aside, if you're a package author, you can hide all this stuff from your user. Right? So in my package for power law stuff, I have a bootstrapping algorithm, and the user just specifies the number of threads, and it does all this stuff behind the scenes, and the user has no idea that it's making a cluster, closing a cluster, stopping a cluster. It all just happens. It just runs a bit faster. In my particular use case, the bootstrapping algorithm always takes a while, so I don't need to worry about is it faster or not faster. It's always a pain in the rear end, so running in parallel is good. So a package author, making this stuff available for your users, it's not that hard. You know, you stick another argument and you just hide it all from them. And because we're using the parallel package, it's all cross-platform. So you don't need to think about Linux and Mac and Windows and all those other variations. Okay? So it's good. Right. Any questions before we move on to the practical? Yes, I have no idea because I can't see anyone over there. But mm-hmm. If you look at the documentation, you can actually specify how it splits it up. So if you start digging in, I'm sure you can specify, do you want it to split it up into chunks of quarters? Or you might think of, well, I don't know how long each thing does, so I'll split the first half into quarters, and then we'll see how things are going and we'll deal with the rest later, but then that's got an overhead. So the sort of standard algorithms you would think off the top of your head that you can tweak. I think it's, if you look for LB, load balancing, under the parallel package, that's what it comes up, I'm sure. And it's just got these standard ways of, the intuitive way you would think about splitting up your group into 4 cores, it's there. And each is upsides and downsides. Yep. You're thinking about sapply and vapply and tidyverse and not using that sort of stuff. It's unstable. I know what you're getting at of, well, sapply, the data type isn't quite checked for, but here I've created the function Monte Carlo. If I can't trust myself, who can I trust? That's possibly not the best answer, but yeah. No. So yeah, you can easily have an extra wrapper function to do the checks if you're getting it from someone else and it's a bit flaky of the types. But you could stick in an anonymous function and have a little if statement, for example. I know it's clunky, but yeah, that's what you've got. Yeah. Oh, yep. How does it compare to, so the question was, how does it compare to for each? I've never actually done timings, and I tend to use them both interchangeably. If anyone knows, does for each work under all platforms? I can't remember. I can't remember if for each works under all platforms. They do it in a different way. I've got a feeling that for each isn't platform independent. It does work under Windows, I think. I'll need to go and double check that. It's a different syntax. So I work under Linux, and it definitely works under Linux. And depending on what time of day it is, depends on which one I use. So, yeah. But is that, so I think that doesn't work under Windows. So I think that's for threading in Linux and Macs. So yes, I think it's a Linux thing. But I'm happy to be, well, not happy to be proved wrong, but I might be wrong there. Yep. So the question is about memory access. When you're running this, and you need to explicitly export things to each core. So there's a function called cluster export, and so you need to be explicit. So it doesn't sort of take a copy of your entire environment. I can't remember if it takes a copy of its smart and takes pointers to each core. I think it's bad for memory. But again, I can't remember off the top of my head. So, yeah. So I tend to do this more for scientific computing. So running lots of Monte Carlo simulations.
Can you nest seamlessly the power supply functions? So you have two, let's say, codes.
Oh, yeah.
How do you handle like the cluster?
Yep. So in general, you wouldn't want to have a power supply inside a power supply. That's just bad. So essentially, it's not magic, and so it's just you're creating lots of threads, and things are not going well memory-wise. So you tend to try and move your parallel part to as high a level as possible. So if you've got two for loops, then try and make the parallel part the outer loop as a general rule of thumb, and the for loop inside is just whatever it is. So, what I'd like you to do, because it's quite easy me waffling on, and you don't really get a feel until you actually do, is if you launch this vignette, I'll put this up for another sort of 30 seconds or a minute, and if people can't get the package, I'll just put the tutorial on this board so you can see. And it's a short exercise of, here's some code, can you run it in parallel? messing about with timings, just to get a feeling for what's happening and see what's going on. If you've got your own code, feel free. The easiest way is just to try and wrap everything that you've got inside a function, right? So do stuff. You've got a function that's just whatever it is, it's just one function, and then does it run in parallel? So again, with the questions on things like memory and load balancing, usually you try it. If it's a problem, then you think about it. If it's not a problem, then don't worry. So have a shot at this tutorial, and we'll do this for maybe about 10 minutes or so, and then we'll finish off with RCPP for the last part. So the tutorial is a wonderful piece of work, simulating a game of snakes and ladders. If you don't know what snakes and ladders are, I think it's got a different name in the States. You can click on Wikipedia. This is based on a real-life example where I got incredibly bored playing it with a small child and actually went and counted up where the squares were in snakes and ladders. So this is the real board game for the £2 version out of a cheap supermarket. So the idea is calling this function snakes and ladders simulates a single game. You're getting back a number, and that's how many rolls of the dice it took to reach 100, all the way to the top. And what I'm wanting you to do is run that in parallel for lots of games. So we're not just interested in one game, we're interested in the distribution of finishing times. So one game is easy, we want to simulate 1,000 or 10,000 or 1,000,000 games, and then create a histogram of the results. Here, I've n is the number of simulations. Choose a value so it takes round about half a second to a second on your laptop, right? Any longer, you get bored and you look at Facebook. Any shorter, you're not quite getting the full benefit. So pick a value of n that's taking around about half a second to get an idea for sort of timings, okay? So this bit of code simulates n games, and so what I'd like to do is rewrite that using parse apply, run it in parallel. Is it worthwhile? Okay, so it's a standard Monte Carlo simulation. And that's how to install the package if you've not got it. Sorry, I forgot to put one thing in the tutorial. As I mentioned, you need to export some of your functions. So doing this half an hour whistle-stop tour of parallel computing, I've just sort of glossed over that part. So here we're doing cluster export snakes and ladders, and that's a function. So by default, when you're taking these clusters, it doesn't copy everything into each of the sort of separate nodes. You need to be explicit. So you might want, so if you're doing lots of things, well, sometimes you might have to explicitly export lots of different functions and variables into each cluster. Right. So line 4 is just us making the function snakes and ladders available to each of the separate nodes that we've created. Right. If you didn't have line 4, when you try to run it in parallel, you'd get the warning or the error message, snakes and ladders not found. Just give you a brief idea of the solution. So line 1, 2, and 3, we're just loading a bunch of packages. Line 4, we're making a cluster. Line 5, we're exporting the snakes and ladders function, otherwise it won't be able to find it. Someone asked, so when you're doing cluster export, you can export entire packages, or you can export multiple things at once. Should you export the entire efficient tutorial package? Well, it depends on how big. Is it going to be done in production, in which case you might want something a bit leaner? Are you just sort of messing about at the terminal trying to get something to work, in which case just stick everything in and fix it afterwards? It depends on exactly what you're doing. So if you're doing it in proper code, then try to be lean, right? If you're doing it in sort of hacky code to get a feeling, then make that promise that you're probably not going to keep if you'll tidy it up tomorrow. So, do that. Then I've just, for timing purposes, and so I could find the bug in my code, I've created two little functions, one called serial, and that's using sapply, one called par, and that's using parsapply. So both doing the same thing. So we can do that. Oh, it's really, having a large font is hard doing this stuff. And here what I'm going to show you is just so you get an idea. I'm going to call the parallel version. I've got a cluster that I'm just using 2 cores. All right, so I've set CL to be 2, and I'm going to be having a ridiculous number of games. Was that 10 million? And so I'm going to call parallel this function, and then if you look, this is my CPU. You can see some lines shooting up. So CPU 2 and 5 are 100%, and now they're dying down. Oh, there's 7 and 5. So you can sort of see it's bouncing up and down, trying to reaching 100%. Not quite. So it's still going to go, and it will stop in about a few seconds. So whatever operating system, you should be able to view your cores. And if I'd put the number of cores to be 8, then I'd have lots of these curves bumping up and down, trying to run as much as possible. And that's me finished the job now, so they're all back down. Oh, no, one of them's still going. Oh, they're still going. Too many cores. Go away. Perhaps one too many games of snakes and ladders. And then we can run it in parallel. What can be quite easy to miss, and I missed it when I was up here doing a live demo, is that we're passing this param to n to each of the 2 functions, which is the number of games. But remember, when you're calling micro benchmark, you've also got the times argument, which is how many times each function's called, and the default's 100. So if you put n to be quite large here and forgot about the times argument, you'd be calling each of these functions 100 times, and you'll be sitting, probably still staring at your laptop for the next half an hour, depending on which value. So something else to remember in the back of your head. You've got 2 ways of expanding how many times you're calling this, and then the value or the number of games you're going to play. Okay. And in my machine for, I think it was 10,000, I got quite a big speed up. So the column to look at mainly is the mean column, right? So it's going from 45,000 down to 6,600. That's microseconds, okay? So it's all relevant, relative. So in this case, for that particular value of n, I got a speed up. If I made n 1, 2, 3, 4, 10, 20, 30, serial will be much faster, and then there'll be a tipping point at which one goes faster than the other. And it's just about finding where that change is happening. So, and then after that, we've got stopping the cluster. Now, 2 tiny things here. You could argue that my timings are a bit fake. I don't know if Donald Trump's talked about fake timings, but it could be fake timings because I've not included the make cluster and the cluster export in my timing. I've done that. That took some time, but then just sort of forgot about it when I did the timings. Right? So we're not quite comparing like with like. So that's something to bear in mind. Again, if you're sort of caring about that sort of level, you've probably got bigger problems. The other thing is you don't need to make a cluster, use it, and then close it. You can make a cluster and then use it multiple times, which is obviously the best thing to do. Right? So if you've got multiple chunks of code that's running in parallel, you can make the parallel cluster once and then reuse that, and that's a nice saving rather than constantly stopping and starting this thing. Okay? Right. So, as I said, I'll stick the solutions online by next week. So the last part, and we've got 40 minutes to cover RCPP. So Duck had 3 hours, so I've got 40 minutes, so it's not fair. So, I'm assuming that you've never used C before, right? So, so we're taking this you've heard about this magical thing that solves all your problems called RCPP. It's sort of the unicorn of the R world of magic happens, but you're not quite sure what C and C++ are, and you've no idea how they interact with R. So what we're going to do for the next half an hour is just get a very, very simple program coded up in C, called through R, just so you've got a feeling for what's involved. Right? That's the aim. Not for you to walk away rewriting the entire code base in C. Right? So sometimes R is just slow. Right? You've tried every trick you know, so you're vectorizing and your code's still crawling along. So you could rewrite your code in C or C++. Right? And we could always do this in R. right, from the beginning. And we could use this function called .call that's available. The trouble with .call is that it's just painful, and the chances of making a mistake are approaching 1 every single time. So it's hard, right? So what RCPP does is it just makes that step easy, right? It makes it easy to write some C code and then call it from R. Right? So have a quick Google for .call later on. It's tricky stuff. So there's a better way. So rather than using .call, we're going to use RCPP. It's a package. I think it's now the number of reverse dependencies is over 1,000 now. So I think it's around about sort of 1,200. Right? So it's a very popular package. And in this chapter, my C and C++ code are largely interchangeable. Right? There's not really a difference between my C and C++ code. That's not, generally true. And I think that link takes me to Stack Overflow, where someone's asked the wonderful question of, is C and C++ the same? And it goes through why it's not. Okay. So my goal here is to give you a flavor of what's possible. This is the rise of RCPP. So x-axis is 2013 time, and it goes all the way up to 2017. And we've got the blue line at the top, that's RCPP, and it's the number of downloads per day, which is probably a dodgy statistic, but it's near enough. And the green line is RJava. The red line here is V8, that's JavaScript interface. And then the one at the bottom is poor old Python, which no one seems to love in our community. So RCPP is one of the most popular packages for doing this sort of language integration out there compared to Python, JavaScript, and V8. So, exercise. So are you ready? So if you can, you should have hopefully installed this before coming, if you got the email. If you can run that bit of code and you get the message, everything seems fine, that means your computer's set up. Okay. So I'll give you a minute, just see if you can run that bit of code, and if you can run that bit of code in theory, RCPP is set up on your machine, you should be able to run it okay. If you don't have it, under Windows you need RTools. Unfortunately the Wi-Fi is not good enough for everyone to start downloading RTools here, so find a new friend who either uses Linux or the Mac, or has got RTools installed for the next half hour. But running that bit of code will test if RCPP is working okay in your machine. I'll come back in a minute. Right, the good news is, if that works, you're good to go. The bad news is, if it doesn't work, there's not a lot we can do about it in the next half hour. As I said, under Windows, you need RTools. Under Linux, it'll just work, because Linux is great. Under Mac, you need Xcode, I think, which you may or may not have, depending on what you've done in the past. Right. Oh, as an aside, if you're building a package that uses RCPP, your users don't have to have RTools or any of that stuff. Okay? It's just if you're developing stuff using RCPP. So for users, you don't, because you've all used packages with RCPP in it. It's just if you're developing code, you need the compiler. Right, so let's have a simple C++ function. Again, I'm going by the idea that you've not seen C or C++ before. Okay, so again, I apologize if you have, but that's what I'm going for. So here's two functions. The one at the top is R. The one at the bottom is C/C++. With your newfound friend, and if your friend's abandoned you, find a new friend, what differences do you see? Right, so I'll just give you another minute. So compare the two bits of code. So the one at the top's R, so hopefully it's vaguely familiar. The one at the bottom is C++. What differences do you see between the two bits of code? Right, they're both doing exactly the same thing in terms of adding two numbers together, but what are the sort of obvious differences just between the syntax? So it's just the syntax idea. So I'll give you a minute to think about that. Talk to the person next to you. It makes it much more friendly. Right, hopefully they're fairly obvious. Normally I would get people to shout out, but it's quite a large room, and I'm too shy to shout out in rooms this size, so I wouldn't bother. So what are the main things? The comment's different, right, in C++. So here we've got, rather than using a hash, we've got /* to start, // to end. You can also do a double backslash to do a comment in C. What else is going on? Lots of types everywhere. Right? So we've got double, 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 and double again, just to make sure we're all on the same page. So double is just a posh way of saying number. Right? It's double precision, so it's just a posh way of saying number. So in C, you get different data types that you need to worry about. You sort of get that in R, but to be honest, nobody cares. It's just all hidden. Whereas in C, you've got doubles that you care about, and integers, and floats, and characters, and these sorts of stuff. But in R, we just go with the flow. We've got an explicit expression of what we're returning, right? So that first double is saying that this function is going to return a number, right? We can't sort of change, right? It's a number. We don't get a choice with that. We've got explicitly what arguments we're taking in, x and y, okay? And there's not going to be any of the funny business where we can sort of look outside scope as well in C and C++, so the scoping's all completely different. The syntax is a bit different. We've got these semicolons at the end, right? There's no semicolons here. I know you can do semicolons in R, but in C, if you don't, you're going to get shouted at and say it won't work. And then the return is just sort of slightly different. So they're similar, but different, okay? And typically, C code is much longer than R code, right? These two bits of code are more or less the same length, but typically, it's going to be much longer than the corresponding bit of R code. So you've got programmer overhead. Right. Also, if you write a C, so if you've got a bit of C code or C++ code, typically we've got a function called main in it. Right? So if I've got a C code that does some Monte Carlo simulation, one of my functions will be called main, and that's required because that's the thing that's going to be run. Sorry. In RCPP, when you're interfacing with R, we don't have that function. Right? So it's more if you're familiar with C, you don't have this function main because you're just calling particular values in, particular functions. What RCPP does is users don't have to worry about platform, compilers, or this RC interface. That's all hidden. Right? So the user doesn't have to worry about syntax of C. That's developers, i.e. your job. Right? You get all the pain and suffering, users get all the fun and games. So that's all hidden. How would we call this function? Right? So here we've loaded the package RCPP, and then we've got this function CPP function. Right? So I'll copy and paste that. Right? So notice that lines 3 to 6 were just that add C function that we had, right? So it's just the same function that you're looking at and seeing differences. We've got the two arguments, x and y. Okay? We've got the value that it's going to be returned, x plus y, and then we've got the return. And if we run this bit of code, right, RCPP has performed its magic. So I've now got a function called RC. Right? So what I've done here is I've written some C++ code. I've put it into R. R's compiled it for us. And now I can call that function directly. Right? So when I call this function add C1, 2, it's taking the numbers 1 and 2, passing it to C code, running, getting an answer, and giving me it back. Right? Which is what RCPP is great at. You know, it's sort of hidden all the hard stuff. Right? You know, what compiler did we use? I'm not quite sure. It just sort of worked. What operating system were you on? Doesn't really matter. It just sort of worked. Right? So RCPP takes care of all that sort of horrible stuff and just lets us get into, we've got some code, we write it, it magically makes that connection for us, which is really, really neat. Right? Now, clearly wrapping all your functions in this CPP function brackets dash would get tedious pretty quickly. Okay? So you'd only tend to use the CPP function for testing your examples like this. Right? It's not the sort of the long-term solution. Okay? So I'll give you, no, I won't give you any time at all. I'll change my mind. Oh, I tell a lie. I do, I'll give you some stuff. If you can try exercise 1 of the RCPP practical. So So running that code will give you some exercises for RCPP. So if you just have a shot at exercise 1, the big clock in front of me tells me I've got 25 minutes left. We'll try and finish in 20 minutes so we can all run and get free stuff before everybody else gets there. So spend a few minutes on exercise 1, and then we'll have the rest. Okay. Right, we'll get going for the last part. I'll stick on solutions to this stuff afterwards. There's another couple of exercises that I'll probably just skip, but there will be solutions at some point. Where are we? Right, so when you're dealing with when you're dealing with C and C++, go away, you need to worry about data types. So these are the sort of standard data types that are in C and C++. So we need to think about characters, that's a single character. Think about integers, floats. So when I was doing my PhD, there's lots of worry about should we use a float or should we use a double. Float takes less memory, so it runs a bit faster, but because it takes less memory, it's not as precise. We've got doubles, we've got voids, they don't need to worry about. There's also pointers, so it's like an address. So you've got these sort of fundamentally different data types that you're trying to sync with R. So some of them are quite obvious, a double, well, that's just a number. An integer, yeah, we sort of get integers kicking about. Characters, we sort of get characters and strings. They're a bit odd compared to this, but yeah, we've got there. But pointers, we don't really do in R particularly often. Voids, nope. Floats, again, not routinely. So as I said, you could use that CPP function to create a C++ function, but that's also going to get tedious quickly. So instead, what we're wanting to do, and the obvious thing is, you've got a script full of R code, and then you've got a corresponding script full of C code, or C++ code. So your C++ file will have a file extension .cpp, okay? And what you essentially do is, you put your C++ code in a separate file. RStudio is fantastic, and so it'll do all the syntax highlighting for you, so it'll understand C, C++. And then what you can do is you can do source CPP path to the file, right? So rather than having this awful hybrid C and R mixture, you have your file full of R code, your file full of C code, you keep them separate, and you work that way. And source CPP takes care of the magic. So what's actually in this C++ function, or the C++ file? Well, you've got that add function that we've come across. Is there anything else that we need? There's one or two extra lines, one or two extra headers that we're going to require. So typically you'll have this thing at the top, include rcpp.h. Right? So this is a file on your computer. So you search your directory, you'll find this .h file. And it's a list of C++ functions that are available. So it's a bit like a library call in R. Right? If you wave your hands, it's sort of like a library call. So your top line of your C++ code is going to have this line that just said, we're going to use all this stuff. Okay? And then the second line is going to be this using namespace RCPP. And the reason why we're going to put that in is because we can't be bothered typing RCPP::. So we didn't have that using namespace. All the C++ functions from RCPP would have to be : everywhere. So it's a bit messy. Okay? So line 1 is typically we want to use RCPP. Line 2 is we want to export all the functions from C++ explicitly to avoid having to prefix them with RCPP::. And then above each function we want to export or use, we have this little funny thing here. So if you're familiar with writing packages in ROxygen 2, you know the tags that you get, you put a little tag above a function saying @export, and it automatically exports the function. Well, this is the same idea. So you put this on the top of each function you want to export. So you've got a function over here that you're wanting people to access, and then you've got a function over here that you don't want people to access. So the one that you want people to access, you stick in / rcpp::export. Okay? So that's just a comment, but RCPP knows it's something special. So with relatively little effort, we can create a C++ file. We've got our 2 lines at the top, include RCPP, using namespace, and then export any function that we want. And that's pretty much it, right? If you look at the dot call, Google dot call afterwards, there's a lot more pain and suffering in it. So the complete file looks like this. So line 1, header file, line 2, exporting the namespace, and then this thing here, this // is just saying we're wanting this function to be available in R, right? If we didn't have the // when we compile the code, it's not available in R, okay? Private and public. And that's it. So that's quite nice. The benefits of using a separate file, you get syntax highlighting, and if you think you make errors just typing code in R, when you've got multiple languages in your head, it's a pain in the rear end because you're constantly mixing up the syntax. Your fingers take on a mind of their own. So at least having them in a separate file tries to alleviate that problem somewhat, right? But if you're anything like me, you're sort of going sort of automatic mode. And by syntax highlighting, you can at least spot that as soon as possible. Okay? We're going to skip exercise 2 and just go on for the end. So vectors and loops. Here's our old friend, the bad mean R function. Okay, so we've got a for loop going along this vector x. X is just a bunch of numbers. We're going to add up each number in turn, divide by n, and return the mean. How would we write that in C++? Well, this is what it looks like here. Right? There's also some RCPP magic in here. Right? Which bits of magic do we have? Well, look what we're passing to this C function, numeric vector. So numeric vector is not a native C type. Right? It's some sort of funny vector from R. What on earth is it? You can't just give that to C. Well, RCPP knows all about numeric vectors, and so we don't have to worry about creating specific types and how to sort of go from one way to another. We just say it's type numeric vector, RCPP makes it all happen and we don't have to worry. Right? And it's the same if we wanted to return a numeric vector, it's all fine. And you can imagine that you get numeric vectors and logical vectors and character vectors and all sorts of bits and pieces. Okay? So RCPP takes care of that communication of R objects into C objects. We've got this square bracket here. So x square bracket I, that looks very R-like. Well, that is R. Right? It's, again, another bit of RCPP magic. So we can do this magical indexing as though it was R code, but RCPP takes care of the translation between C and C++ and R. So that's quite nice. So we can just put this in a file and then source it. Again, you need to have those headers that we talked about. The include, the using namespace, and the export. Right? So let's do a quick comparison. Right? People are beating this to the wine. So we've got mean x, that's base R. We've got the mean version of the R function. Okay? And then we've got a new C variant down the bottom. Okay? So we've got the three functions. The base R version of mean, optimized for the last 15 years. We've got our R equivalent, and then we've got a new C++ equivalent in the bottom. And this is a box plot. So again, time is on the y-axis. It's on a log scale. I think I can't remember the units, so we'll just say it's relative. That's the one on the left is the base R function. The one in the middle, would you believe, is the R code version. And then the one on the far right is our C++ version. And it's not as fast as the highly optimized base R version, but it's not bad. Right, it's doing quite well. The optimized version also calculates the mean in a much more clever way. Right? The downside is we had to write the silly thing in C and C++, right? And that's a big overhead, especially if you don't know another language. If you don't know the language, right? Suddenly thinking of, oh, I'll just rewrite this bit of code in C++. That could be a major task. Right? You might be lucky, and it might just be a few lines of your code, but it might be something else. And the last bit that we'll talk about is C++ with sugar on top. So here's another bit of C++ code, and this bit of code calculates residuals. Okay, so the difference of squares. So what we've got is we've got two vectors, x and y, right? And we're going to do the difference between x and y and then square them. Right, so you're going to work out the residuals. right? The difference of squares. And we've got some C++ code, so we're going to do a for loop. N is going to be the length of the vector, so we've got n things in each vector. We're going to go through each element in turn. We're going to do x minus y, and then square it and raise it to the power. So to do powers in C, you need to use this function POW. All right? So this is C++ code. And it's not that bad. Right? Again, you can see the C++ magic. We've got residuals. It's a numeric vector. And RCPP just makes that understandable to see. It knows what a numeric vector is. The sugared versions allow you to write C++ code almost in the style of R. Right? So this is C++ code, and we just have to write x minus y, comma 2, raising it to the power. So RCPP's even got this idea of we can write vectorized code that you're familiar with. Right? So this will be faster than the R version. It's only 1 or 2 lines, and it's quite nice. This typically isn't faster than that, right? Because there's some thought process going on behind, but it's not much different, right? And RCPP's got so many things and so many examples. One of the nicest things I like about it is if you're wanting to call random number generators. So the nice thing about R is it's got lots of cool random number generators. It's in every single distribution you can ever think of. RCPP makes it really easy to call R code from within C, right? So you can do it the sort of, you can get your R code to call C that then calls R, that then it gets a bit confusing, but it's quite neat. So you can get C code that calls random number generators from R, but then returns the answer. Right? So you don't need to recode every single thing, because recoding lots of random number generators could just be a bit too much. Right? So it's got some really nice features. It does have the potential to speed up your code. It can make it go as fast as C code, would you believe, because you're rewriting it in C. But there is a serious overhead in your time and effort of rewriting it all. So that's what I'm going to finish with. We've got 4 minutes left. So thank you very much. As I said, I'll put solutions to the exercises. A few exercises that we skipped in the last part, just with time, and I'll stick them up hopefully in the next few days. Any questions, please feel free to ask now or grab me afterwards or throughout the week. So thank you.